Next, we have John Gibbons, NA-OBJ from Case Western Reserve University, going to be talking about Grape version 2.
Okay, sharing this screen here. Okay. There we go. And you should be seeing, hopefully you're seeing the, are you seeing the presentation?
Yes, you are good. And we hear you too. Okay,
good. My name is John Gibbons. Currently have an amateur radio, amateur extra N8OBJ. I was licensed in 1991. I'm currently the lab director at Case Western Reserve University's Sears Undergraduate Design Lab. Before that, I spent 20 years of my career at a small little company in Solon called Keithley Instruments. My specialty there was low current measurements. I did the analog design for an instrument of theirs called the KI 6517B electrometer. I also did a lot of the analog design work for their DMM 7510, which is a 7.5 digit touchscreen DMM that they came out with a couple of years after that. So I've got a fair amount of analog design experience under my belt. This talk, I want to specifically delve into the logistics and how the grape actually works, because there seems to be a lot of confusion. So no further ado, the grape itself is a very, very simple receiver, and receiver is probably an overstatement because all I'm really doing is using a Gilbert cell, which is a SA612 mixer chip, and I'm just taking the antenna input with a little bit of filtering and feeding a local oscillator, which is derived from a Leo Bodnar GPS-DO directly into it. And the Gilbert cell is a nonlinear product mixer, so you get sums and differences of the two mixed frequencies. So I then take the output of the Gilbert cell and feed it into a gain stage and do some bandpass filtering, and you get two outputs from it. The A plus B is outside of the bandpass, because for the, say for example, I'm looking at WWV 5 megahertz, I'd be having a 5 megahertz input on the antenna. The local oscillator would be at 4.999, which I'll get into why we did that later. So your sum product ends up at 9.999 megahertz, where the difference product ends up at a kilohertz. So that's the basic operation of the radio. So it's really just a low IF stage mixer. There's not really upper sideband or lower sideband components to this because we have a carrier. So basically the way the Gilbert cell works is if you place your local oscillator below the beacon frequency, that in this case would be WWV, for example, 5 megahertz, we would place the beacon frequency below it and you get the Doppler shift spectrum showing up right here. Then in this vertical line where I'm indicating 1 kilohertz, this line moves with the Doppler shift. So this is the actual frequency coming out of the mixing stage. And it is a 1 kilohertz tone because for WWV 5 megahertz, we're putting the local oscillator at 4.999 megahertz, which is 1 kilohertz below. So the mixed difference comes out at 1 kilohertz. And we're using that, measuring that 1 kilohertz signal to measure the Doppler shift of the carrier for WWV. So this is how it works for the spectrum on how it shifts, which is this line would move over to the right with a positive Doppler shift and moves to the left if you have a negative Doppler shift for the frequency beacon shift. If we actually place the oscillator above the beacon frequency, we actually get a mirror image of the Doppler shift coming out of the IF mixing stage. Now this tends to be non-intuitive because what happens is right around the center frequency here, if you have a positive Doppler shift in the beacon frequency, it's going to show up as a negative shift coming off of the image of the Doppler shift in the spectrum, so that this line would move backwards for a positive Doppler shift. So that's not really very intuitive and confusing. So for Our measurement system, we have the choice of using either the positive or negative spectrum. And our reference point is where the two ideal signals would end up mixed together, which in our case is 1 kilohertz. So for the Grape 1, we use the lower IF, or I'm sorry, the local oscillator was set to a kilohertz below the beacon frequency we're looking at. So for 2.5, we had set the local oscillator to 2.499 and so on and so forth, so the different beacon frequencies. Now the Grape 1 only did 2.5, 5, and 10 megahertz. The Grape 2 is going to add 15 megahertz to that. And if you start looking at the math, you're going to see the challenge I'm having is that this difference here maps right into this guy here, and then these two differences here maps into this one here. So I might have to move these a couple of kilohertz to get the products from not interacting with each other. Basically, for our mixer, we're going to be running the local oscillator 1 kilohertz below the frequency of the beacon of interest. We also will be supporting CHUs 3.33 megahertz, 7.85 megahertz, and 14.67 megahertz for doing Doppler shift measurements on that. This is the Grape Gen 1 receiver. Real quick, this is the voltage input, which is DC, anywhere from 6 to 18 volts. I have a diode in here to protect from people putting the power on backwards, which happens more often than you believe. And I won't mention why I put it in there for personal reasons, but it does work. This is a low dropout regulator, which creates a 5-volt signal that runs the op amp and the mixer. This is the antenna input stage. We have here what's called the TVS protection, or transient voltage suppression. It's basically a back-to-back zener. It presents a 2 picofarad load as an open circuit, and when it hits 10 volts, it clamps. This is helpful for local lightning strikes and for local transmissions of protecting the input from getting overloaded. I added a 1K resistor here, which is a resistive bleed off for if you have a wire antenna up in the air when you wind, it creates static electricity, and this creates a DC path to get rid of that. I then go into a resonant LC filter here. This is selectable jumpers for either 10 megahertz, 5 megahertz, or 2.5, and I'm using a little analog trick here of a 10-to-1 ratio of feeding the signal in on a larger cap, and this creates a sort of a transformer action, so I get gain in here with the resonance. I feed that directly into the mixer straight off. The Leo Bodnar basically comes in, and I attenuate the 3.3 volt peak-to-peak signal into a 400 millivolt peak-to-peak signal, AC couple it into the oscillator input here. It comes out. I do some bandpass filtering here, and this is a gain stage op amp, differential amplifier with a gain of 22 dB with a low pass filter of 2 kilohertz. And this feeds out into a USB sound card that's resident on the Raspberry Pi. This is a picture of the actual board. It measures 1.5 inches by 0.88 inches. It's a double-sided board. This is the input connector here. This right here is the input protection diode. This is the resistor bleeder. These are that's the die or the capacitor input for the LC filter. These are the inductors here on the top side, and these are the other inductors on the bottom side to make the correct values. You put the jumper on for what frequency you want to detect. It goes through the capacitive coupling. This is the mixer. And coming right down here, this is the Leo Bodnar plugs in. We do the division, and this path goes straight into the mixer pin, so you can see it's nice and short, so it doesn't radiate too much. And you'll notice on the layout that this is all ground covered, and this is open such that the LC filter isn't gotten or does not have issues with resonances of capacitive coupling to the ground plane. The output of the the mixer goes into this gain stage. This is the op amp, the output filter, and then the audio out comes out here, which then goes through a cable to the USB stick on the Raspberry Pi, running a version of FL Digi that I modified to create the graph data that is stored every second and every day. Now, Grape Gen 2 is going to be based on the Gen 1's testing that showed that that the receiver was sensitive enough to actually receive the signal, and that we could save data and get meaningful information out of it. And it gave us the target of, we were trying to accurately measure the Doppler shift to 1 millihertz of deviation, which on a 10 megahertz signal is, with a 10 to the 7 hertz, with 1 millihertz, that's a 10 to the minus 10 or 10 to the minus 11, I'm sorry, 10 to the minus 11 sensitivity of 0.1, I'm sorry, 1 millihertz. So it's down to 10 to the minus 10th from that. So we are using that design to move forward since it has worked. The next generation Grape is going to have 4 channels. They're all going to be sampled simultaneously on a clock that's generated by the GPS-DO we'll be using that John Ackerman just talked about. We will be measuring 2.5, 5, 10, and 15 megahertz simultaneously, although you have the option of measuring the WW or CHU channels as well as the WWV channels. And the sample rate is going to be at 8 kilohertz for each channel at 16 bits. And it's important to note that this 8 kilohertz sample rate is critical to be accurate, because that is how we're determining the frequency. So if this is running too fast, it's going to push the samples closer together, and it's going to make the signal look like it's lower in frequency. So there's a direct correlation to having this accurate and having everything else work correctly. This is a block diagram of the actual radio section that's going to have 4 of in the Grape Gen 2. This is the new part here, which is John Ackerman's clock, GPS-DO based clock system. The only other difference between Grape Gen 1 and Gen 2 is this has a little bit of an additional buffer here, because the resonant filters are going to interact with each other, and the other 3 sitting on the same antenna line are going to look like a dead short at the one frequency that this is resonant at, so we have to separate them. But everything else in the chain is pretty much the same. So we plug that all together, we get into a bit of an eye chart, but these are the 4 Grape receivers, radio receiver channels. This is John Ackerman's GPS-DO signal creating the 4 reference frequencies. He's also going to be creating, it's really going to be a 128 kilohertz signal that I'm going to divide by 16 to create the 8 kilohertz sample rate. And he's also giving us the 1 PPS signal, which we're going to feed into the Raspberry Pi 4, along with the communications to the GPS unit itself. We're going to turn the Raspberry Pi 4 into a Stratum 1 clock time standard. So we'll be able to claim that type of accuracy. In addition to these 4 channels, we're also adding the local temperature sensor and a remote interface that has a remote temperature sensor and the remote magnetometer, so we can do magnetometer data measurements as well. And as you can see, the signal comes in from the antenna. We do some filtering and some buffering. It goes to the mixer, creates the 1 kilohertz tone, goes to the ADV channel 1, which comes up here. We sample all those and we suck it into the Raspberry Pi on a once per second epoch data collection. So that's basically the architecture we're moving forward with. It's just basically an expanded version of my test beds of the original Grape 1 design. Now I want to get into real quick what a typical fingerprint day's data looks like. And on this graph, the red line indicates signal strength, which is shown here in relative dB power. And this is in the evening, and this is typically daytime. This is a 2.5 megahertz plot for a typical quiet day. And when the sun rises, you see this Doppler shift right in here, showing that the reflection layer is dropping in distance as it dissolves with exposure to sunlight. And as it drops in distance, it causes a shift in frequency up in the measured Doppler frequency. And you see this is 0.5 hertz on a 2.5 megahertz signal. So that's the total Doppler shift we're looking at. Then the signal drops down, the layer for 2.5 megahertz dissolves due to sunlight exposure, and then the signal drops. And then in the evening, when the sun sets and the sun stops irradiating the part of the ionosphere that causes the reflection, the signal comes back up. The layer expands up in distance and we get a downshift in frequency here. So that's a typical fingerprint of what the 2.5 megahertz looks like on a quiet day. To get a little bit noisier day, you can see during the evening when the signal strength is very strong, we're getting a good signal. You can see that the Doppler shift in black of the received signal is all over the place. And this is due to activity in the ionosphere causing these shifts in height, causing the shift in measured frequency of the beacon. Now, if we move on to a 5 megahertz day, you can see the pronouncement of the Doppler shift at the dissolving of the layer and signal strength is much more pronounced. So during the evening, at night, we have a nice strong signal. And you can see that the thing here stays pretty much right around 0. This is 0.25 hertz. So this is typically within 5 to 10 millihertz of the actual beacon frequency. And there are days when this is actually much quieter, but the reason I'm showing this one here is when the sun rises, it dissolves the layer again, the distance of the reflection layer goes down, which causes the path to decrease, which gives you a Doppler shift up. And that's what this hump here is. It's a very prominent hump shown for the 5 megahertz. Then during the course of the day, the signal is gone. Then in the evening, with the sun not exposing the ionosphere again, the shift goes down because the path length is increasing as it forms. That's for a quiet day. Now, we look at a very noisy day. You see the sort of the same pattern in signal strength. You see the Doppler shift down here and the Doppler shift up here, but you also see all this gyrations of the frequency off of the carrier being moved around by the ionosphere. But this fingerprint of signal strength and then the bump here, this and the bump down is typical for 5 megahertz. Now this is where things get really interesting. 10 megahertz, completely different beast. You can see here that during the evening with no signal strength, we're basically sitting right on the money. And that's because the signal strength it's strong enough to be able to measure, but not much is going on. At sunrise, this thing snaps up. And this particular portion right here where the Doppler shift is positive is showing that the path length is indeed coming down because the reflection layer is being created, not dissolved by the frequency. So this frequency here shoots up. But you'll notice that there's a general trend during the entire day of this line that has this continuous slope, which sort of tells me intuitively that the reflection layer for 10 megahertz is very high in the atmosphere because you get a 0 Doppler shift dead center of the day, and that's not over Cleveland because the Cleveland sunset is right in here. So it's very high in the atmosphere. We start up with a Doppler shift that the thing keeps moving and the Doppler shift keeps moving down, which tells me the path length keeps increasing. And at the end of the day, you get this shift here when the thing dissolves and then it pops up and the signal thing drops off. So that's very characteristic of 10 megahertz. We have this gradual Doppler shift down, and it's consistent in a lot of the graphs, and you see that all the time. For a noisy 10 megahertz day, you can still see the pop up here where you have the Doppler shift and the downward trend, and then the Doppler shift back here. But you see during the night hours, there's enough activity going up in the ionosphere. They're actually getting a very strong signal coming through, and you can see the perturbations of the offset of frequency as it goes along during the evening. So 2.5 and 5 megahertz are nighttime bands that we hear here in Cleveland, Ohio, and 10 megahertz is the daytime band. Again, showing this, we see this is basically daytime for Cleveland and nighttime for Cleveland. This here,
2 minutes.
Thank you. This here is for 5 megahertz. You see it as a nighttime band and then it dissolves during the day. And we go back to this, and for 2.5 is also a nighttime band and it dissolves during the day. And with that, do we have any questions?
Thank you very much, John. Diego, do we have any questions for John?
They were all pretty much answered in the chat already.
He got off easy.
That doesn't happen.
Yeah, I know one of the questions that I answered was people were wondering what happens if you live in Europe and you don't have a local 10 megahertz time station. What if you need to listen to a different time station?
I believe there's, Christina could probably answer this better than I can. There are other time sources around there that you can listen to. It doesn't have to be WWB.
But the thing I noted was that you can actually reprogram the GPSDO
Yes,
to choose which frequency you want. So you can use this at different places around the world.
correct.
Yeah. And then, yes, go ahead, Gareth.
Oh, no.
I mean, Diego, go ahead.
Someone just asked, when will the hardware be generally available?
Yeah, I'm actively in the design phase right now of incorporating the A to D channels and the input filter buffer. So I'm hoping to have working hardware, at least the first prototype, by this summer. And probably in the fall, I'm hoping to have stuff ready to go, but that's my ideal timeline if I don't run into technical problems. The challenge of this design is going to be running 4 radio receivers that are harmonics of each other in a very close space. So I might have to move some frequency around so what we're measuring doesn't overlap and cause problems with the next receiver. So that's my design challenge, and the intent is to have something going by this fall because we want to get ready for the April 2024 lunar eclipse, which is what this whole project is set up to be measuring.
And that's for the Grape version 2.
Grape version, correct.
So the Grape version 1, there is hardware. Some people have prototype hardware available.
Correct.
And one thing we need to be very careful of is John is currently our sole designer and our sole producer of these things. And we need him to focus on the design of Grape version 2. So
Right.
We're trying to keep his load as light as possible from supporting Grape version 1. We are trying to get a few volunteers on board who will be able to help people who would like to build a Grape version 1. We do have those plans posted on the internet, but we're trying to get up a couple volunteers up to speed to help support people who would like to build their own version of Grape version 1.
Yeah, Grape version 1 was a prototype that was intended to test the concept of how this would work because we didn't have any idea, even if the receiver was sensitive enough to receive WWB. And then unfortunately for me, it worked too well, so we ended up deploying it in several places. And it's kind of a kludge. It's not really intended for being out there, but it's perfect for a ham. It's pretty simple to build if you're used to soldering surface mount parts, and I don't want to kill the time here. But I have a bill of material that I had tried to share on DigiKey, but DigiKey only allows you to share within your own group. So I'm going to be modifying the bill of materials that you can order parts. The board itself costs about $6 from OSH Park. If that's about $7 shipped, you get 3 boards, and the parts to populate the board is roughly $25. But the Leo Bodnar GPSDO is 140. The case is about 15. The SD card's about 15. Cables and the USB stuff is about 15. So you get an idea of what you're talking about, Russell, if you want to get into this. But it was never really intended to distribute that, but for a ham project, it'd be perfect to do.
Yeah. So when we get those volunteers up to speed, we'll make an announcement on the HamSci list.
Yes.
So that's where that is. We are working on that. Thank you so much, John. I really appreciate it. I'm looking forward to the new design.